Hey, welcome back to chemistry, and we're continuing on our look at molecular orbital theory. So what we previously looked at was we looked at how the simplest atoms like hydrogen, helium, how you can take two of those atoms and bond them together and create two molecular orbitals. And now we're going to go into more complex molecules. What we're going to do is we're going to look at elements in the second period. How for any particular element we can take two of them, bond them together, and form molecular orbitals. And what we'll see is the molecular orbitals are a little bit more complicated than the ones we got for hydrogen and helium. So let me just reveal a little bit about how we figured out the kind of molecular orbitals we got for hydrogen and helium. So oftentimes you'll see a diagram that describes how you get molecular orbitals. And so I'm going to do one for hydrogen and helium. So if you have a single hydrogen atom, it will have one electron in its 1s orbital. So helium will have two electrons in its 1s orbitals. If, say, you had two hydrogens stick together, they will form two new orbitals called molecular orbitals. Same thing with heliums. They will stick together and form their molecular orbitals. They're both the same in each case. So let me show you how you go ahead and draw out these molecular orbitals for hydrogen and helium. So a lot of times you'll see a diagram where you'll start out and say we have a 1s orbital here, and then from another atom we have another 1s orbital here. And so we use this as a starting point to understand the two kinds of molecular orbitals are formed. So from these two atomic orbitals, we form two molecular orbitals. When these atomic orbitals add together or add constructively together, we form something called the bonding orbital, which is lower energy. So I'm going to put this here, and this bonding orbital happens to be of the sigma type, and it's created from 1s orbital, so I'm going to put 1s like that. Now, we also know that not only can you add these two atomic orbitals, we can subtract them. And when we subtract them, then they undergo a destructive mixing. And so they create the antibody orbital of higher energy. So these are sigma 1s star orbitals. And so the star just indicates that this orbital is an antibonding orbital. And so that's pretty much all we needed for hydrogen and helium. And so you might remember with hydrogen, the two electrons filled up the sigma 1s orbital. With helium, we have four electrons. Two filled up the sigma 1s and two filled up the sigma 1s star. Okay, now we go into the second period of elements, and it gets a little bit more complicated, unfortunately. So we have figured out how to make molecular orbitals for hydrogen and helium when these elements bind together to form diatomic molecules, H2 and He2. Now you're going to have to do the same thing for elements of the second period. So what are the molecular orbitals that form when two lithium atoms bind together to form Li2? How about for two beryllium atoms to form Be2? And then boron, carbon, nitrogen, oxygen, fluorine, neon, what kinds of molecular orbitals are formed from those atoms to form the molecules? Like, for example, with oxygen, how do we take two oxygen atoms and create the molecular orbitals that are involved in the molecule O2? And so that's what we're going to have to kind of figure out next. So what we have to do is, if we're in the second period, we have to figure out how the atomic 2s orbitals from different atoms mix together, and how the atomic 2p orbitals mix together. And so the 2s orbitals, how they mix is really pretty easy. And so how they mix for the 2s is very similar of how the 1s orbitals mix. So for example, when you're getting into the second period, say beginning with lithium and the beryllium and so on, you're going to have electrons in a 2s orbital. And so here I'm just going to write out a 2s orbital here, and I'm going to write another 2s orbital here. Now notice I'm drawing it higher in this picture because I'm saying that this is an energy diagram. And so the energy is going up. Now, what are the two kinds of molecular orbitals that form when you have two s orbitals to bind together? Well, one orbital that will form will be the bonding orbital. It'll form by adding the 2s orbitals, or constructive interference from the orbitals. And so this will be called sigma 2s. Now, if we subtract the 2s orbitals, we'll get a higher energy antibody orbital. So it's going to be called sigma 2s star. So these are similar to the 1s orbitals. And also importantly, they're very similar in appearance. So let me draw a few pictures here. So you might remember what the bonding 1s orbital looks like. So here we have a single orbital that encompasses the two nuclei of the atoms. And they could be hydrogen atoms or helium atoms, for example. So for example, a bonding orbital looks like this. So this is the bonding orbital here, the sigma 1s orbital. The antibonding orbital, you might remember, looks different. Here, because we have destructive interference, basically the area in the middle between the nuclei of the atoms cannot hold electrons. So there's no electron density there. So we have to have separated out orbitals, although the electrons can be here. Now, what do the bonding and antibody orbitals for the sigma 2s and 2s star molecular orbitals look like? They look exactly the same as that for the molecular orbitals for the 1s and 1s star. So the sigma 2s is a bonding orbital just like the sigma 1s. It's just going to be a bit larger. And so the sigma 2s antibody orbital is going to look like the sigma 1s antibody orbital. Again, it will just be somewhat larger. Okay, so now that's how the s orbitals of the second energy level mix to form the molecular orbitals. Now we have to talk about the p orbitals, and the p orbitals is a real pain, unfortunately. So the reason why p orbitals are painful is because they have a different shape than, say, an s orbital, but also there are three of them oriented on three different axes in space. And so let's just look at how atomic p orbitals look like. So let's say you're looking at an atom. It's not hybridized. It's a single atom, and it's just by itself. It's not hybridized. What would the p orbitals look like? Well, let's draw some axes in space. So here we have an x-axis, here we have a y-axis, and here we have a z-axis. And so you know at this point that one p orbital is going to be oriented on the x-axis. I should have drawn those equally. I didn't do a very good job of that. One p orbital is oriented on the y-axis, and then we have a p orbital that's going to be oriented on the z-axis. So I have one lobe heading out toward me, and then with a dashed line, I'm going to show one going into the glass board. And so here are three p orbitals. Now we have to talk about how is it you can have a set of p orbitals on one atom and another set of p orbitals on another atom, and then when those atoms form, the p orbitals mix together to create molecular orbitals. So let's talk about how that process happens. So what I'm going to do is I'm going to bring this up on the computer because I have to make some notes on this. So here we go. So now what I want to do is talk about how molecular orbitals are formed from two atomic p orbitals. And so the first p orbitals we're going to be looking at are p orbitals oriented on the x-axis. And so we have two p orbitals here. And so one p orbital, say on the left, is from one atom, and so I'm sort of highlighting the nucleus of one of the atoms. And so the other p orbital is from the second atom, and so here is the nucleus from the second atom. And again, I think what you can see is that here both these p orbitals are aligned on the x-axis, and therefore what we're doing is we're said to be mixing them end to end. Now, when you mix these two p orbitals end to end and create two molecular orbitals, what do those two molecular orbitals look like? Well, they're described over here. So one molecular orbital you're going to get is where you add these two p orbitals together and you get, for the most part, constructive interference. And so when that happens, you create a molecular orbital that is called a bonding orbital. So it's kind of interesting to look at that bonding orbital because to me it looks like a piece of candy in a wrapper. But you can sort of see here, this is where one of the nuclei are, and this is where the other nuclei are. And you can see that here there is going to be electron density in the space between the two nuclei. Also, we have a little bit of electron density on the other sides of these nuclei. Also important to note is that here, this is an energy diagram. So I'm going to draw an axis here with energy. And what I want you to notice is that this bonding orbital has lower energy than the atomic orbitals it came from. So at the same time that these atomic orbitals can mix together constructively to form the bonding molecular orbital, they can also mix together destructively to form the antibonding molecular orbital here. And so what you can see is that its appearance is different than the bonding orbital. So there's one big difference that you'll notice. Notice in the bonding orbital that we have electron density here that can be found between the two nuclei. And the reason is because what we did is we added this electron density that was found in those two lobes together, and that just reinforced the electron density between these two nuclei. But here, when we form the antibonding orbital, we do not add these two areas of electron density. What we do is we subtract one from the other. So when you subtract one from the other here, what will happen is that the electron density will cancel out, and you'll find no electron density in this area between the nuclei, which I'm marking now in this antibonding orbital. In fact, this area here of no electron density between these two nuclei is called a nodal plane. Now, one other thing to notice is that the antibonding orbital will always have higher energy than the atomic orbitals that it was derived from. One thing I want to do now is talk about the names of these orbitals. So here with the bonding orbital, you can see it was derived by mixing together two p orbitals in the second energy level. But also I want you to notice the basic shape of the orbital. And so what I want you to notice here is that between the nuclei here we have an internuclear axis, and what you can sort of notice here is you have as much electron density heading up out of the internuclear axis to the surface as you have going down or even going out. And so it looks like the electron density is cylindrically symmetric about the internuclear axis. And so that defines the orbital as being of the sigma type. So this is called a sigma 2p orbital. Now the antibonding orbital, it looks a little different. And so what we're going to do is we're going to have a different name for it. So one thing, again, this antibonding orbital is derived from mixing together 2p orbitals. So this is also a 2p molecular orbital. However, what we're going to do is we're going to indicate that it's an antibonding orbital of higher energy by having an asterisk here in the symbol. And also, this is a sigma orbital as well. And so the reason is this. We can draw an internuclear axis here. Now, even though there's no electron density here in this region between the nuclei, if you just go to one side of it, you can see that still what little electron density is there is cylindrically arranged around the internuclear axis. And so this designates this orbital as a sigma orbital as well. Okay, so now what I want to do is talk about how is it you can take two atomic p orbitals that are oriented on the y-axis and form molecular orbitals from them. So this is a little different. So here we have two p orbitals on two different atoms. These p orbitals are oriented on the y-axis, so you can draw a line up like that, just to remind you. That is where the y-axis is, and that these p orbitals are aligned on that y-axis. And you have the nuclei here. I'm marking the nuclei of the atoms there. And so what you can do is you can merge those two p orbitals that are oriented on the y-axis together to form two new molecular orbitals. And so like before, you'll get a bonding orbital, which I'm putting a box around, but also you'll get this antibonding orbital. And so let's talk about what the shape of the bonding orbital is. What is going on is when you form the bonding orbital, you're merging those two p atomic orbitals. They're undergoing constructive interference. And when you bring them together, you should end up with more electron density than you had originally. So we have more electron density here in this area that is below the nuclei, and then we have more electron density in this area that's above the nuclei. Now, one thing that's also important to notice, and so we have these kind of two blobs of electron density that are either above or below the nuclei. But notice we have no electron density in a blob that may be closer to us than the nuclei, nor do we have electron density that is further away to us from the nuclei. So really, we only have a couple of blobs of electron density in the bonding orbital in particular areas of space. So now let's talk about what we're going to call this orbital. Well, this orbital was derived from merging together two p orbitals, and so it's 2p here, but this is not a sigma orbital. And the reason is this: for this to be a sigma orbital, what would have to happen is that you would need electron density that is cylindrically, symmetrically arranged around the internuclear axis, which I just draw. And that is not the case here. We have a blob of electron density up above the nuclei. We have another blob below the nuclei, but we really have no continuous density around the internuclear axis going from above to the below blob. And so this is not cylindrically symmetrical. And so we can't call this a sigma orbital. We have to call this a pi orbital. And so we call this a pi 2p orbital. Now let's take a look at the antibody orbital here. When you merge these two p orbitals that are oriented on the y-axis, not only can they constructively interfere to form the bonding orbital, but they can destructively interfere to form the antibody orbital. So imagine these red areas here in the atomic orbitals and these blue areas here being brought together. You're merging them together, and now when they merge together, they will destructively interfere. And so in that area, you will have no electron density here, and so you'll find that is a noble plane. But as it turns out, due to the mathematics, what will happen is you will get electron density, and they'll be in these kind of blobs that are kind of shoved out from the nucleus like that. So one atom here with its nuclei has blobs of electron density, and same thing with the other atom with its nuclei, and has sort of blobs of electron density that are shoved out. Okay, now also this is not a sigma orbital, and the reason why it's not is because we do not have electron density that is cylindrically, symmetrically arranged between the axis that occurs between the two nuclei. You can see that we have some electron density that may be above the nuclei here and below the nuclei, but we really don't have continuous density leaving above the nuclei and going to below the nuclei. So this is not cylindrically symmetrical, and so we have to call this a pi orbital. And because this is an antibonding orbital that was formed by destructive interference, we're going to designate this a pi 2p orbital, but we're going to put an asterisk here to indicate that it's an antibonding orbital. Now, the same thing can happen with two atomic p orbitals that are oriented on the z-axis. And so here we have the two atomic orbitals. They're both p orbitals, and so there's a nuclei here and a nuclei here. And you can see that the lobes of density are aligned on a z-axis that is maybe heading out toward me and then heading into the board. And so when you merge those together, you get two molecular orbitals like you got before. One of them will be the bonding molecular orbital, and one will be the antibonding molecular orbital. The ones we just saw where we mixed together two atomic p orbitals that were on the y-axis. Now we're mixing together two atomic p orbitals that are on the z-axis. The appearances of the molecular orbitals are the same, it's just that they're oriented in space a little bit differently. Now what's going on is in the bonding orbital, what you have is that you have these blobs of electron density, not so much above or below the nuclei. You have blobs that are, say, between the nuclei and me, and then you have a blob of density between the nuclei and the board. So anyway, this is not going to be a sigma orbital, and the reason is we don't have electron density cylindrically arranged around that internuclear axis. So this must be a pi orbital. And same thing with the antibody orbital. There the nuclei is here and here, and we have an internuclear axis here. And as you can see, that the electron density is not cylindrically arranged around that internuclear axis. And so this is a pi orbital as well. And I want to get some practice drawing these orbitals. And so what I might suggest you do is, as I'm drawing these out, you might want to draw them out too, so you get sort of comfortable with drawing what these molecular orbitals look like that are derived from p atomic orbitals. So the first thing we're going to do is we're going to derive the molecular orbitals that are formed from the two p orbitals that are oriented on the x-axis. So I have a nucleus of an atom here, and so here's one p orbital, and here's, well, this is one p orbital there. Here's another nucleus of another atom, and so this is a p orbital from there. And so what I'm going to do is I'm going to mix these together. So you would shove them together and you would add up the electron densities. Now, can you draw what the bonding molecular orbital and the antibody molecular orbital look like? Well, the bonding molecular orbital would look something like this. Here are the two nuclei, and now here you're adding them. So you're going to increase the electron density between the nuclei, and so we have this sort of shape here. And then we have a little electron density on the other sides of the nucleus. So this is the bonding orbital for px, and it is called sigma 2px. Now, can you draw the antibody orbital? Okay, a little bit trickier. So here's the nucleus, the antibody orbital. Again, if it's an antibody orbital, there's going to be an area between the nuclei where you cannot find electrons. So this is a nodal space. And so we have a little bit of density here and more density here, a little density here and more density here. So this is the antibody orbital for 2py, and it's called sigma star, 2px. These are x p orbitals, not y, x. And these are called sigma star 2px. Now, what I want to do next is draw out how the p orbitals oriented on the y-axis overlap. So we have here one p orbital here and another p orbital here. And so they can mix together. They can do it constructively to form the bonding orbital. So let me show you that. So here are the two nuclei. And so you might remember you'll get density below the nucleus and density above the nucleus. This is no longer a sigma orbital. This is a pi orbital. So this is pi 2py, and this is a bonding orbital. Now, can you draw the antibody orbital? That's a little bit trickier. So here are the two nuclei. You will not find any density between the nucleus with antibody orbitals. Instead, you get these lobes that are kind of shoved out like this from one nucleus, and then this one is shoved out from this nucleus. And so this is going to be an antibody 2py orbital, and it's a pi orbital. So that will be its designation. Now, you can do the ones oriented on the z-axis really quick. So let me just do that really fast. So imagine the p orbitals going out in the z-axis. So here you would find some electron density heading out toward you and some electron density going into the board for the bonding 2pz orbital. So this is called pi 2pz. Now, what does the antibody orbital look like? Well, this is going to look like a lobe kind of heading out toward you, and then another lobe going into the board, and then this other nucleus, a lobe heading out toward you, and another lobe going into the board. And so this is the antibody 2pz orbital, so I'm going to put a star there. Okay, so that's a lot to know. So I would suggest practicing these things on your own and try to get sort of used to what the shapes of these molecular orbitals are. Okay, so now we're going to go back to the computer and point out another thing that you need to know.